Hi, so in today's lesson, we're going to be looking at the applications of Newton's third law of motion. And Newton's third law of motion states that action and reaction are equal and opposite. Or you could also state it as for every action, there is an equal and opposite reaction. So now we're going to look at the application. First, we're going to be looking at the recoil of a gun. Now, you have a gun. I'm actually poor on drawing. I can't draw. I'm sorry. So you have this gun, and then you have a bullet. Of course. Now, if you take a look at this diagram, of course, the mass there is the action going on in the gun. The reaction is the bullet coming outside. You see it now. The gun has a mass. Capital, let's say M1. The bullet has a mass, let's say M2. Now, the bullet, after the gun has been shot, the bullet is going to be moving with a particular speed, let's say V2. Now, this gun would go now the gun is moving forward, isn't it? Gun is moving forward. So the bullet is moving forward. The gun is moving backwards. That's why there's always precaution when you're handling the gun that you shoot it, So there are trainings because in order to handle the recoil of the gun, because when the bullet goes forward, the gun has to go backwards. It has to be balanced. Now, the recoil of the gun, that means the rate at which the gun recoil, is called that V1. Okay, so according to our law of conservation of momentum, that M1 V1 must be equal to M2 V2. But now, because this is in opposite direction as this one moving forward, this one moving backward, then this has to be minus. Now, if that's the case, then if we actually calculate the recoil of the gun, then I have to divide both sides by V1. Sorry, M1 rather. So that means the recoil of the gun, V1, is actually minus M2 V2 over M1. So this is the recoil of the gun. This is the recoil. That's the recoil of the gun. Now the negative here just shows that it's in opposite direction as the gun. So it's not. So if you have, let's take an example. Let's say you have a gun that weighs, let's say mass of gun equals 30 kg, and the mass of bullet weighs about 0.5 kg, and the bullet is moving, velocity of bullet, the speed of the bullet is moving at, let's say 10 meters per second. What's the recoil of the gun? So let's call that recoil. What's the recoil of the gun? So now the recoil of the gun has to be the mass of the bullet multiplied by the velocity, mass of bullet multiplied by velocity of bullet divided by the mass of the gun. Yeah. So that's going to give us V equals 0.5 multiplied by 10 divided by 30. So this cancels this. And so we're left with 0.5. That's half multiplied by 1/3. Okay, and that gives us 1/6. So this is the recoil of the gun. Alright, so that's the recoil of the gun. So now we're going to look at another application, is the operation of the jet. The operation of the jet. Alright, so the second application that we actually want to talk about is the operation of the jet aeroplane and rockets. So how does this work? Now this basic idea works with the principle of the balloon. So you inflate the balloon with air, then when you release the air just from the tip of the balloon, the balloon moves in the opposite direction. So the air is coming out in this direction, the balloon is going up in this direction. So that's the principle at which the rocket engine works. All right, so how does this work in reality? So you have fuel that is burning at the exhaust. So there's a particular mass and the rate at which they are burning. So the rate at which the rate at which the fuel is burning makes this rocket engine to move forward. So this is the action force. This is where the action is taking place. Burning of fuel, action force, and coming out with a action force, and this is the reaction force. Now this is actually called forward movement or forward thrust. Let's call this forward thrust. So it creates a forward thrust. Then the jet, so this is the jet of hot gas. So that's where the gas is being exhausted from. So the burning of fuel, creates the rate at which fuel is being burnt and coming out. So that outward action gives us a forward reaction. So let's see an example. Let's say that a jet engine is burning fuel at the rate of, so it's burning fuel at the rate of 0.4 kilogram of fuel every second. And it produces a force at the exhaust. It produces a force of, let's say, 120 newtons. So that's the force that it produces when it burns 0.4 grams of fuel every second. Now the question is that what is the velocity that is going to be produced at the exhaust? What's the velocity? Remember that when we do momentum, it has to be mass and velocity at the action must be the same as the mass velocity at the reaction. Now the only thing we got the force, we get the rate at which fuel is being burnt at the action, but we don't know the mass and we don't know the speed at which they burn. So that's what we're looking for. Okay, now remember that they gave us this as kilogram per second. That is mass over time. That's what they're telling us. Mass over time. And that's 0.4 grams kg every second, every 1 second. Now, and they give us force. They gave us force to be F, and the formula for force is ma. F equals to ma, right? And if that's the case, remember that when we are proving the Newton's second law of motion and the relationship between impulse Ft equals to mv minus mu. So we got that formula to be F equals to be m, then v minus u over t. I believe you can still remember this formula, isn't it? Good. So I can actually rewrite this by saying F equals to mt, then v minus u. I can write this as this. So remember that we got m over t as what? 0.4. So then I would write this as F is what? F was our F? Our F is 120. 120 equals m over t is actually 0.4. Then we now have change in v. That's a change in velocity. And that's what we're looking for. And so if we divide both sides by 0.4, so what should you get? So then our v has to be 12 divided by 0.4, and that equals to 300 meters per second. So that is the speed. That is the speed at the end of the jet engine. Okay, good. So this is just basic application for Newton's third law of motion. So we're going to be looking at examples on how to solve questions relating to application of Newton's third law of motion. Okay, good.